So the idea of today's session is to try and sort of kind of give an overview of what these new Cadenza challenges are all about, and to give you a chance to kind of ask some questions and hopefully help you enter the challenges. So I've got a few of my colleagues around the room, and you'll meet some of them as we go through, and hopefully you'll find this a really useful session. You'll notice the URL there, which has all the information that you could kind of need about the project. So the agenda for today's Q&A is that I'm going to give you just a brief overview of the project. I assume someone is letting these people in as they kind of appear, because you do that, Gerardo, as we go.
Yeah, I'm monitoring that, not worry.
Thank you very much. And then we're going to have a look at which tasks we're actually looking at, sort of overview of them. We'll have a Q&A at that point, just about the general principles of what's going on. And if you want to ask questions, feel free to type something in this chat as we go along, or we can kind of unmute and chat. We're not going to be a very big group today. Then we're going to move into Gerardo, who's going to show us some tutorials around the baseline software and talk about that. And again, we'll have another Q&A at the end. So that's the kind of process we're kind of going to do today. So for those who don't know, we're very lucky that Cadenza is a project that's been funded by a UK funder called EPSRC. And we have a 4.5-year project that's in its second year, done about a year. And the whole idea of the project is to try and improve music for people who have a hearing loss. And we're doing that for a series of challenges. We call them machine learning challenges, but you can think of them as signal processing challenges if you prefer not to use machine learning. But the whole idea is we're going to have a series of these over 3 series of them over these 4.5 years, and through each round using different scenarios to try and look at better ways of trying to make music sound better for those people who have a hearing loss and have to listen maybe through a hearing aid. Now, the background for this project was a project that Alinka Greasley led called Hearing Aids for Music. And I'm going to pass on to her because it gives a context for why we would want to run these challenges. So over to you, Alinka.
Great, thank you. Well, yes, as Trevor said, here at Leeds, I've been leading a project called Hearing Aids for Music, and the purpose of the project really was just to understand how hearing loss and the use of hearing aid technology affects music listening and performance. And so we did a project that had a number of different studies. There was a sort of a clinical survey with patients, a survey with audiologists about the strategies that they use to address musical needs. There was an interview study, and then there was a big national survey as well. So we're really mapping the differing effects and experiences of people with hearing loss who use hearing aid technology. And what we found, if you want to move the slide on, Trevor, is actually that people were experiencing quite a range of problems, and as you can see listed here, some were pitch perception difficulties, so difficulties with hearing out certain pitches, particularly in the high frequencies where there's more likely to be loss. Reports of music sounding out of tune and discordant, and difficulties with picking out different instruments as a result of reduced frequency selectivity. Our patients also talked about problems hearing lyrics within music, and a lot of people do like to hear the lyrics when they're listening. So for them, not being able to decipher the lyrics, to understand them, was a key part of their musical appreciation that was missing. They talked about lack of clarity, or sounds blending or blurring together, sort of linked to the difficulties with picking out instruments as well. Our participants talked about poor sound quality and the introduction of artifacts with hearing aid use. So, for example, feedback and distortion. So elements of the sound that weren't there originally that are being introduced by use of the technology. They talk about difficulties with dynamics and volume change, and difficulties in live settings as well. So it's kind of a range of different problems. Now hearing aids do help. They help with the audibility. They help to hear out different instruments, and they are reported to help with lyrics. But as hearing loss gets more severe, those difficulties are more pronounced. And if Trevor, if you move the slide on, there's a graph here that just really summarises some of these some of the issues that the hearing aids they do help. They help to make music more audible and help with hearing out the different elements of music. And you can see here that the modal response in both pre-recorded and live settings is 8 out of 10 for the helpfulness of hearing aids. But if you take an average, it's actually 6 out of 10 for both of these settings. So the hearing aids help, but they do actually cause difficulties as well. And on the next slide, you'll see just I've pulled out some of these difficulties here that are reported by participants that are relating to dynamics and compression strategies, to frequency range, automatic functions that are implemented within hearing aids for speech perception, and problems with sonic artifacts and sound quality. And I'm just going to pick out a few quotes on the next slide for you. So, for example, our participants were talking about a reduction in sound quality when they're wearing their hearing aids. So this sort of sense that they do allow me to hear more in the music, but overall the quality is poor. There were others who talked about spectral balance, so quite a few examples of hearing aids making the sound too trebly and accompanying sort of accounts of music being tinny or too harsh. So you can see here, again, with hearing aids, the music comes to life, but high frequency sounds may be harsh or edgy and voices do not sound natural. And another participant saying the device seems to have too much treble and not enough mid-range or bass. So there are numerous comments in the in the studies about issues with spectral balance with the hearing aids. As I said, sonic artifacts as well, so feedback and distortion that's being introduced by the hearing aids that was reported to negatively affect appreciation, and in particular be really frustrating in performance contexts. Some other, Trevor, if you move the slide on one, yeah, some other reported problems with the technology include issues with the compression strategies that are used in the hearing aids having a negative effect on dynamics. So sort of reducing the volume in different ways when the listener's experiencing music. Problems with also with the adaptive functions for speech, so things that are put into hearing aids to make them just to improve speech intelligibility and perception, such as the feedback manager and the noise reduction manager can actually have a negative impact on music by changing the volume, the dynamics. So as you can see from the quotes here, we've got participants that are saying, well, sometimes my hearing aids will think a musical note is feedback and suppress it, or my hearing aids will misidentify music as noise and then reduce it. So what we have here is particularly in live settings a situation where the hearing aids are actually sort of producing quite a variable output for the listener. So really what that's suggesting is that we need different signal processing for speech and music within the hearing aids. And this is not a new problem. We've known this for some time, but the manufacturers have prioritized speech perception over time rather than music perception. Now that the manufacturers have implemented specific music programs within hearing aids, but our participants and also those in other studies, such as those done by Valerie Loy and Weisberg in the US, have actually found mixed evidence. So some people say that the music program improves their musical experience, but others say that they can't tell any difference between the music program and their everyday speech program, or the other end of the spectrum, that the music program actually has a negative impact on their musical experience. So there's something about the the music programs that are not are not currently working as well as they could do. We don't actually know what's happening in these music programs in terms of the algorithms, but what we do know is that we need different signal processing for music, and really this was the backdrop to the project, which is wanting to better understand how we can improve the signal processing for music for people with hearing loss. Okay, so back to you, Trevor, on that.
Yeah, so thank you very much, Lincoln, and it was a nice link back. And to say with Cadenza, I think what we're looking at here is can we use some of the modern machine learning and signal processing tools that are around to improve how the audio quality of music for people with a hearing loss? Because there's a lot of techniques out there being published, but mostly they're not applied to this group. And it's a large group. There's 430 million people worldwide who have a significant hearing loss, and that number is growing as the population ages. So what I'm going to do is go and look particularly at the sort of kind of just a rough overview of the challenges we've set, the 2 tasks we've set this spring. And I think I wanted to pin down, first of all, what we're actually looking to improve. And we've talked about the perceived audio quality. And I think the best way I've found to sort of describe this is just imagining you've got the same music track and you're listening to it, say, on a cell phone with a really horrible MP3 rendition, or you're listening to it in a studio with high quality monitors, and evidently the music is the same, but the audio quality is very different. And so what we're trying to do is we're trying to improve that reproduction quality. We're not interested in musical preference, what people like, maybe people with hearing loss prefer some music over the other. That's not what we're about. We're actually about how can we reproduce the music better. And that could be about remixing or reprocessing the music in kind of any way that you feel kind of fit. To give an obvious example, lyrics has been mentioned. Maybe we do the equivalent of speech enhancement to make the lyrics more intelligible. So up on the website, we've had some dates, and we've actually had a slight update on these dates, or a firming up to be clearer, because they haven't really particularly changed. And I actually haven't changed the website yet. So we have currently 2 tasks, which I'm going to describe in a moment. We're going to be releasing the evaluation data right at the end of June. And then we have a couple of weeks where we're going to be taking submissions in July. And what we're expecting there to get submitted is the audio that you've processed, and you'll see what that is in a moment, and also a technical report, so we can see how well have you complied with the rules. And then we've got some objective evaluation. We'll look at that in a second. But I think one of the big things we're organising is a listening panel, which will be running in early autumn. So we'll have people who are used to using hearing aids, who have bilateral hearing loss, I mean they've got hearing loss in both ears, who will be listening to the samples you produce and scoring them for their audio quality. So we'll have subjective evaluation as well. And then at the start of December, that date isn't firm yet, but I'm roughly working towards 1st December, we will hold an online workshop where, with these typical challenge workshops, we'll present results and teams can present what they've done and that kind of thing, and see what we can learn going forward to future challenges. Those are the dates. I will update the website and put those on firmly when I get a spare mo. So what are the 2 tasks this time? So the first one, task 1, is about listening over headphones. So Alinka was talking there a lot about hearing aids, but there's an awful lot of music reproduced that doesn't necessarily need hearing aids. So that we're going to get the headphones to do the amplification the hearing aid does and anything else. So you don't have the kind of thinking about a hearing aid here. It's just how do we make the sound over the headphones as good as possible, considering the listener characteristics. So in all our systems, you will see we have a sort of random listener, and that's pulling out a listener with particular hearing characteristics in terms of their audiogram. So that's the threshold of hearing. And of course, we're going to be pulling out music here as well. And we have an enhancement stage, which is essentially the processing within the headphones, and then we have an evaluation stage. So your task in this is going to be to work on the enhancement stage. And as you can see in this block, what we've done is we've set this up as a demixing, remixing task. And there's a couple of reasons to do this. One of the reasons is there's a big community working on demixing, so we can tap into their expertise. But also we know from work on, say, TV sounds, that if you can demix the music tracks, it allows you to remix them in different amounts to make it better for people with hearing loss. It takes some very simple example. Once you've demixed it, you could take the vocal track and make it louder if you want to make the lyrics more intelligible, for example. So what we're looking at here is demixing into the sort of standard vocal, drums, bass, and other that you get in demixing tasks. There's left and right channels here because it's stereo. And then remixing it down here in any way you want to go to the listener. And we have two stages in the evaluation. We first of all have the evaluation using Hacky, which is an objective measure of audio quality. So you may, when you've done demixing tasks and previously use some sort of signal to distortion ratio, but we're using Hacky, which allows for the hearing ability of someone with a hearing loss. It's a correlation measure which does sort of kind of compares the demix signals to the original in a correlation, but also has an amplification stage to allow for amplification that normally happens with hearing aids. And then the actual final remixing task will produce stereo signals, which are what's coming over the headphones, and then that's going to go to the listening panel, who will actually do the listening here. Now, we think most people will be doing this sort of mixing, demixing work, but actually, if you've got an idea to make headphones which just replaces this entire block and produces an interesting stereo signal in some way, we're happy to see entrants that kind of do that as well, if that's what you want to kind of do. But we're mostly expecting people to follow this kind of process. So your enhancement, we're talking about decomposing the signal is what you've got to submit. So you're going to produce those 8 stems, left and right, vocal, drums, bass, and other, and you're going to produce one stereo signal, which is going to be the remix version. This is obviously for each music track, and we're expecting you to try and optimize the processing for each listener. So for that reason, in the data, we give you the audiograms. We also give the music data set to work from. This one's commonly used in demixing tasks. And also we've given you some suggestions for data augmentation as well in the system. And then in the evaluation, this part is the fixed code. You'll process the evaluation data set, which we will provide at the end of June with listeners with audiograms that we will provide at that point. And we'll have this objective evaluation using this metric called Hacky, and also you'll provide us a remix stereo that will go to a listening panel. Now, there's quite a few terms I've thrown around there, like Hacky, which you may or may not be familiar with. And I just wanted to point out that on our website, we actually have quite a lot of information about this stuff under the learning resources. So we have the challenge specification, but also on the top here, you've got learning resources, and you'll find lots of things here. So, for example, we have here a talk by James Cake describing, I mean, he and his colleague came up with Hacky, and he describes here objective measures, and also we've got down below this bit, scrolling down, actually how Hacky works as well. So if you want to know a bit more of the background of these measures, the detail is up there. But I'd also encourage you to ask us. We know that people are coming to this from different backgrounds. Maybe this is the first time you thought about hearing loss. If you're confused by something to do with hearing loss, hearing aids, or whatever it may be, please feel free to ask us as a team. Put something on Google, or obviously on Google Group, or obviously ask us now. The other thing I would say is we talked in here about doing some remixing. We also have some information in this sort of kind of learning resources about intelligent sound mixing, which is a whole field of how you get a computer to automatically do remixing. There's some more material about to go up there. I haven't quite finished editing a video from a colleague about it, but here's a Q&A with one of the Cadenza team, Bruno Fazenda, about what is the intelligent sound mixing community doing and what techniques might you be able to take for this headphone task. So that's an overview of the first task that we're doing. The second task is listening in a car. So you can imagine a scenario where you're sat in your car driving along and you're listening to sound coming out of the car stereo system. This is a slightly more complicated baseline in terms of its evaluation. But basically what you're trying to do here is make the car stereo processor. So you're going to be fed music, stereo signals, which are being fed into the car stereo, and your job is there to process them. So when it goes into the car and there's noise added, actually sounds as good as it can be. So that's your job, is to make a better car stereo processor. Again, it should be tailored to a particular listening ability, so there'll be an audiogram for each one. What you have, as well as knowing the listener and their hearing abilities, and also knowing the music, we also have metadata on the driving, which the reason we give that there is that tells you some characteristics of the noise. So this is a bit like, if you've ever worked on speech enhancement, it's a bit like speech enhancement, because what you're doing is saying, how can we make the music best as possible given the presence of the noise? And so we're giving you, obviously extracting data like the RPM of an engine is something that could be readily done in the car. So you'll know something about the actual noise that it's going to be working against. So you get this metadata as well, which gives you some statistics on the noise, but we're not giving you the detailed temporal fine structure. This is not an active noise control task. So that's the enhancement stage. So what we will be submitting is the process music in here. So you're providing this car stereo processor, and your listener is going to be wearing a simple hearing aid, and we will provide that. When you see this thing called NALAR, that's a hearing aid amplification algorithm. We're providing that, a simple linear version of that we will be using. That's to give audibility. So the code exists, and you're not meant to touch that. And as I said, you have access to the car metadata like the speed, so you know the rough spectrum of the noise that you're having to deal with. Again, we're providing music tracks across 7 music genres, listener characteristics, and this metadata. And the one thing that happens in the mixing is we are setting an SNR ratio. And so we're saying, given a particular SNR ratio, what can you do to the music to make it sound as good as possible? Now, that has one slightly unintended consequence. Well, we knew it happened, so I don't know if it's unintended. It means if you just make the music louder, the noise in the car goes up. So you can't actually just make the car noise insignificant by blasting the noise at the person sat in the seat. You have to think more intelligently about how to process the music than just make it louder. But obviously this change in level is not actually what would happen in reality. But it's because we've given you an SNR budget. This is kind of done in speech enhancement tasks as well. Here's the evaluation stage, which again, you're not touching, and basically it's simulating the car. So if you think about you're playing sound out of the car stereo, you've got the transducer response, loudspeaker response, the sound going through the car, so you've got the acoustic of the car, you've got the car noise to add, it's interacting with humans, so you've got a head related transfer function HRTF to model, and then you've got it going into actually a hearing aid. We're providing all of that. You don't have to worry about it, but this simulation here is doing all the, how does sound get from the loudspeaker to the person's ear, is done in this block. And then we provide, as I said, the hearing aid that is fixed. You're not changing that. So there's a fixed hearing aid. Again, we'll evaluate using this correlation metric called Hacky again, but also we'll be sending this also to a listening panel as well. So it's fixed code. Gerardo will show you a little bit of it, but this is all kind of fixed, but it's doing the acoustics of the car noise, the HRTFs to simulate the ear. It sets the signal to noise ratio. As I said, that is fixed. And then it processes the music and noise through the hearing aid. The one thing you need to be careful there is you don't blast things so loud that you clip the hearing aid, but that should be okay. And as I said, you've got 2 evaluations. So that's a kind of overview of the two kind of tasks and the project. We've got Gerardo coming in to talk a bit about the baseline system, but I thought it might be useful here, rather than just talk at you for a very long time, to ask at this point whether you had any questions about the general things we're trying to approach, or any comments that you'd like to make. If you've got questions, feel free to stick them in the chat, or if you prefer, you can unmute or put your hand up. There's a question there about what testing data we're providing for task 2 and what does it look like. So in the task, what we'll be providing in the test, in the data, which is released at the end of end of June is we're providing a set of audiograms for our listening panel. So there'll be 50 audiograms for our listening panel. So that's the listener data. And then we'll be providing a set of tracks. I'm going to have to look at Gerardo to remind me exactly how many there are, but there's 30-second long tracks in the evaluation or test set. How big is the evaluation test set in task 2? I forget, Gerardo, sorry.
Yeah, so we have a large budget for the number of songs, but we need to narrow down the number of songs. But we will provide, like in the training data set, we will provide the scenes. So that means all the information that you already have for the training. So the SNR, the hearing aids, the song, the listener, the head rotation angle. So it will look basically the same as the invalidation set, for example.
Epri, does that answer your questions sufficiently? So we still got to decide how many we're having in the evaluation set yet.
Okay, and also I have a question. So can I use the noise generator and then kind of, because in the evaluation you will add the noise, right? So can I just like the music subtract with this noise, and then because in the evaluation you will add with this noise again, so in the evaluation the music will be kind of clear. Isn't that the purpose of this challenge?
So the challenge isn't about trying to do active noise control, because in the end you don't have the temporal fine structure of the noise. So you won't be able to subtract the noise from the signals to try and extract what, you know, a clean signal. But if we show you the baseline again, you do have access obviously to start with. We just show it to you.
Sorry.
That's all right. Let me just flip. Sorry, it's just thinking about presenting. So if we look at the baseline here, you do actually have access to the clean music. These two tracks should say the same thing. They're basically the same thing. So what goes into you already know the clean music, so you don't need to do a subtraction to get it. But what you don't know is the exact noise that is going to be added in this simulation. What you know is metadata about the noise. Did that help answer your question?
Because in your metadata you provide a pair of listener and the scene, and then what type of car noise parameters, because I thought I think I can I just generate this data and then just kind of subtract and then in the end add it to
so there's nothing. I'm not quite sure the question exactly here. I mean, I think there's nothing stopping you using the generator to work out the statistics of the noise algorithm. That's absolutely fine. But if you look at what's available when you're running the eval set, you won't have access to the actual noise signals, because the actual noise signals is generated in this block, which is part of the evaluation, and this is all fixed. So you don't actually have the fine structure of the noise.
So can I say like it's kind of equalizer in this enhancement? So whatever the car speed is getting faster, the music will be getting higher than the noise, kind of like that.
Yeah, so if you take a typical car stereo that currently happens, it's not designed for people with a hearing loss. One of the things they do is apply a dynamic range compression. So they basically compress it so it's louder than the car noise, and the volume coming out of the car stereo varies with the speed of the car. But there are other techniques that you see in speech enhancement that you could kind of think about. So one thing they do in speech enhancement is find the energy where the speech is and suppress that, and then sort of kind of play the music which is outside the speech range louder potentially, is the sort of kind of thing that you could think about doing, is finding a bit of music which is important that isn't going to be swamped by the noise and amplify that. So yes, an equalizer, it could be about trying to change the frequency response of the music in some way.
So yeah, so this is not an anti-noise cancellation, right?
No, it's been deliberately set up as not a noise cancellation task.
Okay.
Okay, I hope that helped. Xander's asked a question. The challenge specifies that we are trying to be improving the enhanced portion of the system, either via improved DMUX model or some DSP approaches. Are we permitted to modify some of the other modules as well, for example, the audiogram or NALAR approaches? So in it depends on the task. So in this task, this hearing aid is fixed, and you can't alter it. So this is entirely fixed. So when you're talking about a change to the NALAR approach, which is stuck in this hearing aid, no, you can't. And if we take the first one, the first task, if I go back to this one here, then when you do your demixing, depending on how you do it, before you send it to Hacky, you will be applying some form of amplification in this point here. Hacky is expecting a NALAR, an amplification like NALAR, so you would probably mimic a NALAR here to maximize your Hacky score. But of course, you're then feeding this into a remixing and amplification stage where you could do different things. So this amplification here from the demix signals is purely to try and match what Hacky does. So Hacky takes the clean signal, applies NALAR, and it correlates that with whatever you give it. So if you don't do a little bit of amplification here, the Hacky score will be slightly lower than you might expect, though it's not that level dependent, that it will be slightly lower. But in here, yeah, you've got free reign. I hope that answers your question, Xander, and if it doesn't, please. So Xander, why are we using NALAR rather than NAL and L2 and all the other fitting functions? So in terms of, and by the way, if you're not seeing the chat, Michael Ackroyd's typing stuff about the car simulator because he made it. Why are we using other techniques? Well, what Alinka sort of didn't go into the detail in her presentation, but when you try and do what we know from hearing aid research is that when you start doing something non-linear with compressors, that's when you can have problems with processing music. So you can get sort of pumping sounds and other stuff going on. So we believe that a lot of music processing within hearing aids is actually to try and not do too much processing in the same way as speech. So I don't know if someone who knows more about hearing aids would like to comment. So we've shied away from doing a non-linear process for that reason, in an effort to sort of kind of try and stop those non-linear artifacts appearing, and done something fairly simple. Within this task one, of course, there's nothing stopping you in this remixing amplification block doing something with a dynamic range compressor as you feel fit, because that's just going to a listening panel. So there's nothing stopping you doing that if you want. I hope that might have answered your questions, Xander. I noticed Bill is typing, and he is also a hearing aid expert. He says, just because we have used a linear compression scheme, it's not trying to discourage you from trying compression in your enhancement schemes. I guess the other reason is if we stick a compressor in there, that kind of limits what you can do. Are there any other questions at this stage? Thank you for the ones you've given so far.
Could I ask a question, please?
Yeah, please, far away.
Thanks. It's about the headphone task. Will the, so for example, for the listening panel people, will they be taking their headphones out, sorry, their hearing aids out to then put the headphones on to listen to the sounds? Or will
Yes.
they keep their hearing aids? They won't keep their hearing aids on.
No, they won't be wearing hearing aids. So everything that they need has to come out of the headphone processing. So they will just wear headphones and listen to things without their hearing aid. So they'll be listening. I was going to say au naturel. I'm not even sure that's the right thing. So you have to do it all on the headphones.
So we would have their audiogram to match it to their listening experience.
Yeah, so if you look on this, I'm still sharing, aren't I? Yeah, if you're looking here, the audiogram feeds into all these sections, so you can use the audiograms as much or as little as you want to try and individualize what you try and do.
Okay, yeah, thanks.
Well, just to come in on that, if I may, a lot of hearing aid users don't actually like wearing their hearing aids and headphones. They prefer to take their hearing aids out because the headphones tend to be uncomfortable, and they also cause feedback. So they don't work well at all. So we had a lot of people in the project saying that they took their hearing aids out in order to wear headphones. So I think that's quite typical of some of the listening experience with headphones.
Yeah. Yeah, thank you, Linky. Yeah, and Xander, yeah, that's correct. I mean, if it's in the evaluation block, basically it's fixed in both those tasks. So yeah, there's no point fiddling around with what's in the evaluation blocks because we're going to use those as fixed. So it's, but there's nothing stopping you use compression anywhere in the enhancement block you think it can help. So there'll be, I think we'll move on to the next stage, which is Gerardo's going to show us the baseline system and talk a bit through that. And feel free to keep asking questions as we go. And so I'll pass over to Gerardo, who's working diligently on producing all the baselines and all the systems we need. Over to you.
Yeah, thank you, Trevor. So yeah, now I will present you some of the baseline code and how you can write and modify it for your own submission. So probably it will answer some of your questions. So first of all, I will like to mention why we are storing our code in the Clarity project, or you need to install it like as a PyClarity module. So Clarity project, they aim to improve speech and intelligibility and quality for people with hearing loss. So that we have similar objectives, but in Cadenza, we are focused on music. So these similarities means we share some of the code-based code, and which makes sense to make it together. And both challenges are organized in a similar way. So what I mean about that is we both mature learning challenges. We both provide scenarios, the data set, the tools, and some baselines. So unifying the code base allows us to simplify the maintenance of the code, so it's all in one place. So for example, the implementation of an oral prescription, and also provides a single entry point for newcomers that probably working on speech and want to move to music, or the other way around. Well, the Clarity project is, and well, the Clarity and Cadenza GitHub is storing a GitHub repository, the code. You can install it just using PyPy, like any Python module. You can clone the repository. And we are releasing versions of this module tagged to each challenge. So Cadenza 1 of this first challenge is tagged to the version 033. Or well, you can install directly from pip install and tag into the version in GitHub. So okay, now we'll go through the baseline of task 1. So in both tasks, we are providing a small package for the demo data. This demo data is just to help you to start running the code and see if everything's working properly. And well, you can download it easily using GDown. This code will can be shared with you later, but it's similar to what you'll find in the tutorials within the GitHub repository. So the demo data can show you where, for task 1, we're providing a metadata directory which have the listener's characteristics, the audiograms, and the list of songs. And in the audio directory, we have, the MuseDB18 tracks. So basically, this is the same. If you have already a copy of the MuseDB18 HQ, you can use that, but we are providing a mirror of that data. So as Trevor mentioned before, so the baseline is divided into 2 stages, the enhancement and the evaluation. You can treat these baselines as a recipe, or in other words, as a template. So everything that is in enhancement, you can modify. So you can run this enhancement and get the baseline scores, and then you can modify anything you want inside the enhancement within the rules of the challenge. And the evaluation is where you can't touch anything, or just keep it fixed. Asking Sander why we are using narral specifically in the enhancement for the task 1 is because the Haki is defined to use narral. But if you want to try another amplification in enhancement, then you can run it over Haki and get your score. And you can see if it's even though it's not the same amplification, you probably getting better score. Some of you may notice that the evaluation is a little bit slow. That is because we are doing several correlation within Haki, and we have full-length songs or tracks in the result from the demixing. So this is why it's so slow. There's not much we can do right now about that, so sorry about. So if we go into the code, in the enhancement, we have several functions. So one, this is the entry point, which is the enhance function, which uses Hydra config style. So you can, it's a very handy tool that allows you to use the config YAML structure. So you can change everything in this config YAML, or using command line to change different parameters for each of your experiments. So this enhance function is basically the function that orchestrates the mixing and remixing in our baseline. In the decompose signal function, is the function that decomposes a single signal into the stems. In the baseline, we have 2 baselines. So one is using the demotes, and the other one is using the open and mix. So this allows us to have 2 decomposition kind of techniques. One based on demotes, based on time domain, and the open and mix is based on spectrogram decomposition. Both are passed to this decompose signal method, plus the signal, the order of the output sources, and we are passing the left and right audiograms. You may notice that we are not using the left and right audiograms in the baseline, but they are there just to show you that you can use it as part of the mixing model. So you may want to train or to try to experiment with a model that decompose the BDBO, the signal into the BDBO output using the audiograms of, in other words, resulting in a narral-like amplification output, instead of having an amplification as a different block. We then have this process stem for listeners. This is a function that takes the 8 stems we get as a result from the mixing from the previous function, the compose signal, and applies the amplification, which is neural in our case. Again, because this function is in the enhance module or stage, you can play with it and modify things. So for example, if you are doing a decomposition that applies the amplification as part of the process, you may not need to use this function at all, because amplification will be already in the output signal. And then we have a function that do the remixing signal. In the baseline, we are just adding the process signal from the previous function. So this function will output the 8 BDBOs mono signals with the neural amplification. And in the remixing, we just add the 4 left and 4 right signals, resulting in the stereo output. We have other 3 functions that are just for utility, which one for separated sources that takes any signal and model and produce the output, with some optimizations in case if there's a memory constraint. Whereas just a mapping function that map the signals with a proper stem name, and when the get device that simply returns the torch device. In the evaluation, this is a simple hacky computation. To make this evaluation fair and constant along all the submission, we have a seeding procedure, which basically seed the function using the name of the song. So it doesn't matter in which order you're computing the hacky, or who is computing the hacky. As long as it's the same song, you will seed the song in the same way. So you will have the same seeding for that song. So everybody will have in the same seed values of order in the randomness in the hacky has. Well, evaluate song listener is just the function that takes the song, takes the listener characteristics, seed the song, or seed the randomness, and compute the hacky. Well, as I mentioned before, we are using Hydra that use this config YAML file. This is how this file looks like for task 1. So we define several paths. I'm not going to go in detail on every single of these parameters, but you can ask any of this if you need to now. But I think it's important to let you know why we have 3 different sample rates here. The first sample rate is the sample rate of the MuseTV 18HQ samples. So the input tracks are 44,100 Hertz. The stem sample rate is the sample rate for the to save the stems, the 8 stems. Why we're using 24,000 Hertz is because hacky, it doesn't matter what is the sample rate you use, hacky will downsample or upsample to 24 kilohertz. So better to save it in that sample rate from the beginning. And the remix sample rate is the sample rate we are asking for this remix signal that will be presented to the listener panel. We start playing with this, so some of you have noticed how we managed to reduce the size of the output signals. So this was part of this process to optimize the output of the signals. So now for the objective evaluation for hacky, we are producing 8 mono signals corresponding to the left and right VDBO at 24 kilohertz each. They are peak normalized to avoid clipping when we are saving that, but we are saving the normalization factor so we can restrict the signal to the original level so we can compute the Haki. They are saved in 16-bit PCM and compressed and saved using lossless flag compression. On the other hand, for the listener panel, we need one stereo signal at 32 kilohertz, 16-bit PCM. We also compressing using the lossless flag, but in this case, the signal need to be within the, if it's in the float, when you're working on that in float, the output should be between -1 and 1. So it's your job to deal with the clipping, any clipping that happens when you're saving the signal. So to run the demo, you can run it using CLI or just calling Python enhance.py, and then passing the path where the data is stored. That will produce an enhanced signal, which in the first level, we have a directory per listener and then a directory per song for each listener. So as you can see, we have the left bus flag with the file which is saving the level, the same with the drums, the same with other, and then finally we have the remix. So I'm not showing here the other 4 signals to make it short. But so basically we have 8 flag signal for left and right BDBO. We will have 8 text files corresponding to the level and 1 stereo remix signal. Then for the evaluation, well, you can play later and hear the samples. I'm just providing some code where you can, using a Jupyter notebook, plot and hear this, display and hear these samples. I'm scared to do it here because it can be probably loud some. But then the evaluation, you can just run the same way, just calling the evaluate.py signal script, again with the same path. And this script will automatically go to this enhanced signals directory, loading each flag file, transform to a webpack, and compute the Haki. Is everything clear in this recipe now? If you want to make a question now, I don't want to go to task 2 if somebody have a question.
I think that's a good idea, Gerardo, to sort of have questions now. There was a question from Xander about why Haki dance samples to 24K, which I've been answering in the chat if he hasn't seen. I think also Haki was developed for hearing aids originally, and I think a lot of hearing aids working at 24K. I don't know if they still do. Bill Whitmore might be able to comment a bit more on that. But essentially, this is again where the learning resources we have might be useful. We've actually got some typical audiograms and description of what's going on. But essentially, the issue is if you take the bunch of people we're dealing with, their hearing loss is so severe, you'd have to amplify things so much for stuff above 12K that you would end up putting it above the pain threshold, or it would be very uncomfortable for them. I had one question for you, Gerardo. Are you planning to distribute the link to this Jupyter notebook?
Yes, this is a Jupyter book, but you can run it or load it directly as a pin binder in Collab or run it live here. it's a little bit slow this, or you can download the Python notebook directly. So yes, this will be together with the video, so we can add the link to this.
Okay,
And
we'll put it on the
can
website.
download it. Yeah.
So another question for Zan about hearing loss. I feel like I don't know if Michael or Bill would rather answer this particular one. So one of the thing about essentially genetic hearing loss, or actually what you described there could be you might get with, say, noise-induced hearing loss. You get dips rather than, so general hearing loss of age is kind of generally a sort of kind of slope doing that, whereas you can get dips from other factors. We have a sort of criteria that we're dealing mostly with age-related hearing loss, and we have criteria to mean the audiograms are generally of this kind of slope shape. I'm sure we will have some which will have some noise-induced hearing loss in them. I don't know if Bill or Michael would like to comment more about why you know, the hearing loss characteristics. Why we're choosing age-related hearing loss, because it's the biggest source of hearing loss. We all, unfortunately, will succumb to it at some point. I already have. So Bill's typing. There's a question.
If I can just expand while Bill's typing, Trevor, I think you've got it. You nailed it in your last sentence. Something like at least half the population will have a decent hearing loss by the time they're in their 70s or their 80s, and it's for that we are essentially starting the first challenge. It's for the most number of people. We fully agree that not everybody's hearing loss is by definition independent. Some people have got more other frequencies. Some people have got genetic codes on genetic hearing loss underneath. Some people have got a proper noise-induced one with a Carhart notch, etc., etc. And we may well be able to consider those in subsequent challenges. But I think for the first challenge, it's worth going after the most important, in some sense, the relatively simple one of an approximately low pass presbyocusis style age-related hearing loss.
Yeah, what Bill was adding there was, if you look at the graph, I did paste it across. There are ones which have hints of notches. They're not completely like a low pass filter. As he was pointing out as well. Sample rate. Sandy also says sample rate affects sound quality in general beyond just Nyquist perceivable frequencies. So because we're evaluating this using Hacky, there's no point in us asking for a higher sampling frequency. And in fact, given the amount of data you're going to have to send to us, you wouldn't like us to ask it at a higher sampling frequency. So that's our pragmatic reason for choosing that as a lower sampling frequency. We've got to remember as well that as you get age-related hearing loss, you get other effects going on as well. So some of the other artifacts like frequency smearing and other things are happening as well. So it's not just a threshold of hearing change. We have a task 2 question, which we might take forward to task 2 when we come to that. April, I noticed there. Are there any specific questions on task 1? Any more questions? Otherwise, we might move on to task 2, and so we can present it and then pick up this question that we have on in task 2.
Okay, so we'll continue then. Yeah. Yeah, well, as you can see, this is the same part. Okay, so in task 2, we had the same structure as a recipe than in task 1. We also are providing a demo data package. So these packages, as well as the official packages, have a metadata again and an audio directory. The metadata here is much more information. So we have the listeners, the same structure than before. So it is a list of listeners with the audiograms. We are providing the a file, which is the information of the HRTFs. We are providing the music, a set of scenes. The scenes is what all the information of the is for the one sample is stored. So we have which song is sounding, which direction is the listener looking at. the SNR at the hearing aids, and then car noise characteristics. And the Sun listeners file is just an indication which listener are set in that scenes at the moment. So why this is separated, because we can have one listener, one scene, and different listeners in that same scene. So they all will have different audiograms. In the audio directory, we are providing the HRTFs. So we need it for the evaluation. So the anechoic and in-car RTFs and the music samples. These music samples are mostly based on the small FMA data set, but we discarded 2 classes from there, which was the electronic and experimental classes, because they were more prone to have very unpleasant music for all people. It's very experimental, but we increased it using with the classes orchestral and classical from MTG Hamendo dataset, using the same procedure that in FMA. Well, as I said before, these have the same structure, so we have an enhancement and evaluation. Each of these stages have one file or one script. In this case, the enhanced script is much simpler than in task 1. It just, the enhancement procedure is just taking the song in the baseline, and we set using loops, we try to adjust the level of the song according to the average hearing loss to prevent some clipping. So if it's too loud, the loops level, we reduce it. So we reduce the clipping of the output song. So, and that is our output. In the evaluation, on the other hand, this is slightly more complicated. So for the evaluation, we are providing a function that evaluates one scene. So with the function evaluate scene, in this function, we are taking the reference signals, which is the clean music, the enhanced signal, which is the signal coming from the speakers, the loudspeakers, sample rate, the scene ID. This is just for saving samples. The current scene information, which is a dictionary, the listener audiogram. In this function, we do the whole process. So in a way to make it simple to understand what is happening, so we first created a class that is called class scene acoustics. This class provides a different method necessary to generate the noise using the parameters given. Apply the HRTFs to the enhanced signals and to the reference signals. I will explain which one is added to the reference, and applies the hearing aid, which is fixed for this task. So as you can see, this class car scene acoustic provides the apply car acoustic to the signal, the hearing aid, get the car noise. So in other words, it generates this car noise. Add the HRTFs and scale a signal to the SNR, to the hearing aid SNR. We are also providing utility class called Audio Manager. This was basically because many things are happening in the evaluation, so we are adding a flag in the YAML config file that allows you to save all the intermediate audio files, so you can hear what is happening in each of these stages, but also is saving by default the reference and enhanced signals will be passed to Haki and to the listener panel. So the reference signals that we will save is, I will show you later, but In the enhanced process, you will produce this enhanced the signal coming from the loudspeakers, and the evaluation will save an hearing aid enhanced signal for evaluation, which is the enhanced signal plus the car noise and the HRTS, and will save the reference signals with the anechoic HRTS, which are both used to compute Haki. We are providing in the code, which is saved in Clarity Usil car noise simulator, not in the recipe itself, two classes. One that generates the car noise parameters, and another that generates the signal itself. As we mentioned before, you can use the car noise signals in the enhancement, but we are providing both classes because you could use it to learn something about the spectral of the noise given the car speed and the gear. So we separated the stochastic with the deterministic part of the car noise into these two classes. The car noise parameters generators takes the car speed input. I will generate all the stochastic or random parameters needed for the car noise, and it will generate this large number of parameters for the filters. You can see in the YAML file. And given those parameters, you can pass it through the car noise signal generator, and you will generate the signal. So we did it in this way because so you can pass these parameters you have in the YAML file, and the output signal used in the evaluation will be always the same. So it is a deterministic at the end, the noise for each scene. So you can play with this, and probably you can learn something about the spectrum, as I say, but perhaps play with the spectrum subtraction, but it will depends only on the car speed and the gear. So it's not the noise itself. Again, the YAML, the config YAML file have the same structure. We are providing some paths that are unique in this challenge, like the HRTF files, which are all in reference to the metadata or to the original path. We have only two sample rates in this case as an output. One is the input, this is 44 kilohertz, and the output of the enhanced signal, which is 32 kilohertz. Why we keep the same 32 kilohertz? Because it's the same signal what we pass to Haki. So Haki will do the downsampling to 24 in the computation, but we will do that. We will use that signal in the listener panel. So you can run the recipe in the same way. So just calling Python enhance.py and the path root. So the demo data will run 20 songs. And as you can see, it's really, really fast. So in 3 seconds, run the 20 songs because it's a very simple enhancement. And so in fact, there's no point to make it sound because it will sound like the original, but you can see in this case, the output will be organized as the set, the listener ID, and the scene ID. And then in the evaluation, this will process all the signals we mentioned before and run the Haki. So here I want to play. So for example, we are here evaluating just one scene. So it's just one output or enhanced signal. But in the evaluation, we are generating evaluation signals. And in this case, I have two for the same scene. One is the reference, which is the original song with HRTFs. I'm not sure it's going to sound. It's a little bit louder in my case. Does it sound? Can you hear it, Trevor? No? Yeah? Okay, brilliant, thank you. Special. And in the, it will also produce this hearing aid process signal. Again, too loud. Probably you can hear the differences because this one has the hearing aids and all the different HRTFs in the music, in the processed music. Is this signal, the HA's process signal, that will be evaluated by the listener panel. So it is. This is why we are saving it also, because you can hear what the listener panel will evaluate, because they want to evaluate directly your signals, but they want to evaluate the signal they hear in the car. I hope that clarifies part of this task. Is there any question about it?
There's been a couple in the chat, Gerardo, while other people are thinking about other questions they have. So the question actually which came earlier on was from Epri was about kind of what's available, and that she wanted to know if the SNR was available, which the answer is yes. So I put into the chat the link to the rules page that lists everything that you can use. I know the website is big and complicated. We've tried to simplify it to make it easy to find stuff, but if there's stuff you can't find, please just get in contact, put something in the Google group, and we'll help you out. But yes, SNR is available. So that's one of the bits of data you can use in the during the evaluation. The second question was a question about LUFS, which I've answered about. In terms of what it is, it's a standard loudness measure. I mean, if you open up something like Adobe Audition and you ask it to do loudness, it will be in LUFS. It's the audio industry's standard method of measuring loudness. It comes back in dB. What is the scaling doing here? So I didn't kind of clock exactly when that was being asked, but we have to scale at various points to make sure we don't have clipping happening with the systems. So there's various kind of points at which we have normalization, also to try and stop you blasting excessive noise at people. So I can't remember exactly. I don't know if you noticed, Gerardo, when the question was asked, but there's a couple of LUFS scalings, aren't there?
Yeah. Let me go back even further. Wait.
It's 1307, this question. It says, also, maybe we already covered this, but what is LUFS? Well, I've answered that in the chat. And what is the scaling doing here? But I'm afraid I was at the time typing answer to another question, so I wasn't quite listening to exactly which normalization you were talking about at that point.
So looking where we are. So that's the sorry, the normalization asking is about enhancement, right?
Well, when you answer that question for that point, if it's not right, he can come back. But yeah.
Yeah. So basically, so we're just doing is trying to keep the signals within -1 and 1. So yeah, here it has. So we try to keep the loudest between -14 and -11 loops when the hearing loss is below 50 dB. So why is that? Because even though we are not doing anything more in the signal here, the signal will be passed to the hearing aid later, and that means they will have some amplification. So we need to prevent that when that amplification happens, is go too loud and distorted for the listener. So you need to keep it. You need to try to keep it in a level that it won't be affected or won't be clipped when you're saving the signal, and hopefully not be clipped later when the listener is hearing the song. So why we decided to use -14 and -11? We started using the Spotify Luft's normalization levels, and then with some experimentation, we try to find a level where the clipping was minimized without just reducing the levels dramatically and being very unfair.
It might be nice just to scroll back to the schematic, and I'll just to make it. That was a really nice explanation. But if you look in the evaluation block in the middle, you've got a hearing aid, and that's a fixed hearing aid, and what that has is an amplification. But if then the signal goes greater than plus or minus, greater than 1 in terms of its magnitude, it then clips. So we need to make sure the processed music going between the enhancement block and the evaluation block is not so loud that the hearing aid causes it to clip. And the amount of amplification you get depends on the hearing ability of the user. So it's not quite as simple as just setting a very standard number. It has to depend a bit on audiograms, the hearing ability. Now, when we set this, we did it a very rough and ready to make sure it worked. I think you can probably, as an entrant, do better than we did in terms of how we normalized it. But our concern was just to make sure it wasn't excessively clipping across all the audiograms we were using. So actually, a better set of the level in the enhancement would probably help you there as well. But that's what we did. I hope that covers that point, Xander. Do shout if we haven't answered it very well. The other question,
no,
I was pretty sure
that does answer it. Yeah, I think that's right. I was just basically trying to make sure that I understood what the scaling to loss. You're essentially mastering it, right? And trying to make sure that everything's right at the right dB level. Is this also designed to, or it sounds like it's also like trying to avoid engaging the compression of the hearing aid too much right out of the gate, because that can introduce artifacts. Is that also part of the purpose for scaling the LUFS?
Yeah, it is, but our hearing aid is linear with a clip, which is the most severe compression you can think of, I guess you could think of it. And so we're trying to make sure it doesn't clip the signals. So the NALR, which we're using, is very simple. It's just linear gain, but it mustn't then go into a range because we have to hard limit things. So it doesn't go above the hard limiter. The other question, which you may have missed, Gerardo, and I was pretty sure I knew the answer, but I wasn't confident enough to jump in. When you generate the car noise, are you using the seed every time so that they can reproducibly compare different methods, or is it random every single time?
So the car noise parameters you have now in the metadata, those were generated using a specific seed, but the noise signal that will be generated is deterministic based on those parameters. So there's no randomness in the generation of the signal because of the random values were generated and are saved in the scene. So the signal you will have in the evaluation is stochastic, it's deterministic in that sense.
Okay,
you can generate different parameters with different seed. We use the same seed for the when generating the scenes, but the signal itself used by the evaluation is deterministic for the same parameter. So the same parameter will generate the same signal every time.
So the answer
is that answer?
Yeah, no, the answer is yes, you can. Therefore, the seeds are set, so you can see in the metadata how to make sure that you test different systems with the same seeds, and therefore make sure that you're doing something reproducible in your comparison. Of course, when we go to the evaluation set, we'll be changing those seeds. But for comparison, yes, you can compare. So do we have any other questions? Well, thanks for your participation and the questions you've provided so far. We will. I'll stop recording this now. What we'll be doing is